Hello, calculus fans. So we know that if we have a convergent series, the partial sums approximate the total sum, S. The question that we want to ask is, how good is the approximation? So the idea is that we need to estimate the remainder. And the remainder we're going to call R sub n. And this is just the total sum minus the first n terms. So this is the tail of the series. This remainder is the error that's made when S sub n is used as an approximation to the total sum. All right, let's go back to when we discussed the integral test and we developed that. Let's assume that we have a series which converges by the integral test, and it's using the function f of x, which is positive, continuous, and decreasing. And of course, the function gives us the terms of the series. So f of n is equal to a sub n. Let's look at a graph. So really, we're just going to think about the tail of the series. So I put a ... here indicating that there's a whole bunch of terms at the beginning that I don't really care about. What I'm most interested in is the tail. And I've drawn a bunch of rectangles, the areas of which are a sub n plus 1, a sub n plus 2, a sub n plus 3, and so on. And so we add all those up, and that's going to be the remainder. Remember that our remainder was the sum of all of these quantities. And that remainder, then, is less than the integral from n to infinity of f of x dx. Go back to that picture and see that the area of those rectangles is smaller than the area under the curve from n to infinity. And we have another picture. Now we're going to place rectangles so that they go above the curve by choosing the heights of the rectangles to be the left endpoint of each subinterval. Notice that the areas of these rectangles, it's still R sub n. But now look at the fact that the area of these rectangles is larger than the area under the curve from n plus 1 out to infinity. Okay, so that's what we're going to express here, that the remainder is bigger than the integral from n plus 1 to infinity of f of x dx. All right, so we have a theorem, which is the remainder estimate for the integral test. So it's the usual sort of thing. It's the setup for the integral test. We have a positive, continuous, decreasing function, at least for x bigger than or equal to n, and the function gives us the term of the series. And we let R sub n be equal to the remainder. That's the tail of the series. And what we've proven now in the preceding two pictures is that the remainder is sandwiched in between the integral from n plus 1 to infinity of f of x dx and the integral from n to infinity of f of x dx. Now, as it turns out, it's the second inequality that's going to be the important one, as it's going to give us an upper bound on the error. That upper bound will be used in later calculations. Okay, that's all for now.